Welcome back to recitation. In this video I want us to look at the following problem. We're going to let f of x equal 1 over x, and I want to consider the solid generated by rotating f of x about the x-axis between x equal 1 and x equal infinity. I want you to find the area of a cross-sectional slice, and then I want you to find the volume of the solid. In the cross-sectional slice, the one I'm interested in is the one that you see in the xy plane. So my suggestion to you is that right away draw yourself a picture, just at least a rough sketch of the curve y equals f of x, and then what that cross-sectional slice will look like, and start off from there. And take a while to work on that, and then I'll be back and show you what I did. Okay, welcome back. Well, hopefully you were able to make some headway on this problem, and maybe you found some interesting things. Hopefully you did. And we will see what I find and if they are interesting, which I think they are. So let's start off. I told you the first thing you should do is get a rough picture, so I'm going to draw a rough picture and make sure that those match up well. My picture matches up with yours. So let me give you the xy plane, and then y equals 1 over x is a curve that at x equal 1, I'm going to make y equal 1 up here. Y equal 1 up there, x equal 1. So when x is 1, y is 1. And then it's going to decay down. As x goes to infinity, it decays. So it looks something like that. And then I actually should have moved this 1 because I'm going to need that side to get my cross-sectional slice. So my cross-sectional slice is going to come down here and look something like this. Oops, that's supposed to be symmetric. That's still supposed to be something like this. It's supposed to be symmetric about the x-axis. And the cross-sectional slice is the area of that. Now, if you remember what you saw in lecture, you saw, I believe, that the integral from 1 to infinity of 1 over x dx diverges, because you end up with log evaluated at infinity, and that is infinite. And so you wind up with this. This actually diverges. That was the area of the top part from 0 to f of x. So of course, if I double that, I'm still going to get that it diverges. So in fact, the cross-sectional slice area, CSS area, is infinite. Okay, so that's one part. The other part is to find the volume of the solid of revolution. So the second part was take this piece from 0 up to f of x, rotate it around the x-axis, and compute the volume. Now we know how to compute the volume. This is the disk method I'm going to use here. And I will write out what we need to do, and then we'll look at what the integral gives us. So for the disk method, so let's say this is the volume part. So the volume, it's going to be the disk method, so I need to do pi r squared. And in this case, I'm integrating from 1 to infinity, so I need pi r squared dx. I'm going to be integrating something that's pi r squared dx. And I know the bounds are 1 to infinity, and so I need r in terms of, as a function of x. That's fairly easy. R is just the measure from 0 up to f of x, so that's just 1 over x. So this is actually the integral, I'm going to pull the pi out, of 1 over x squared from 1 to infinity dx. Okay, so how do I do this integral? Well, you were shown in class that in actuality, this is the limit as some value up here goes to infinity of this integral, but we're just going to do it the shorthand way that he also mentioned in class and keep the infinity around. So we can keep that as our bound, knowing we're taking limits as this thing goes to infinity. So the integral of 1 over x squared is negative 1 over x, so I get minus pi times 1 over x, evaluated at 1 and infinity. I can just check that if I need to, but this is x to the minus 1, and its derivative is negative x to the minus 2. That's why I needed that negative there. And then I evaluate this. Well, at infinity, 1 over x, as x goes to infinity, this first part goes to 0. So this is 0 minus negative pi times 1 over 1. So negative pi times 1. So this is just pi. Okay, so hopefully that kind of blows your mind a little bit, that you could have something where this cross-sectional slice is infinite, but in fact, if you look at it, the way we computed the volume, we have, in fact, a finite volume. So I don't know what else I'm going to say about that, except I think it's really cool. And you can think about why that is. And in fact, you might want to notice that we computed things in terms of cross-sectional slices coming from the other direction. So we looked at these cross-sectional slices, and we showed our volume was finite there. So we had a sum of a bunch of finite things, and so it made sense that you were going to get, and the finite things were getting small fast enough. That's the point. That when you add up these finite things that are getting small fast enough, you can still end up with a finite number. But I guess, yeah, that's where I'll stop. So just to say that we were looking at this sort of solid of revolution problem again, but we were dealing with improper integrals, and we were showing how you can do these kinds of problems with improper integrals. So now I really will stop there.